what we've established is that we've got this short period of time to get this Holocene like Anthropocene, but a lot of the scientists who were in that room sort of came together and they said, well, what does that actually mean? What do we have to accomplish? And that is really the basis of the planetary boundaries. So while they define the planetary boundaries and the all the literature and comms around it as the safe operating space for humankind, what it really is what do we need to have a Holocene like Anthropocene? But of course that's not so catchy, right? So the way the planetary boundaries works is that the sort of scientists went out and said, what are the mission critical environmental impacts at a global scale that if we go beyond a particular threshold, we could fundamentally change the state of the planet. So this isn't looking at every single environmental impact. You know, in New Zealand, we've got some pretty bad soil erosion, for example, which is a major local problem, but soil erosion is unlikely to have sort of catastrophic global impact. So they went through and looked at what are the things that could have catastrophic global impact. And then for each of those components, they said, what do we know is the safe limit? Now, with scientific studies, there's always a bit of uncertainty when you're looking at geological periods and total global change. The zone of uncertainty can be quite big. So if you're looking at this diagram, the blue circle in the middle or green in the middle is the where we're really sure that we're unlikely to change the planet. Then there's this zone of uncertainty where you can see some orange between the blue circle and the red circle. Sorry, my cursor's on the wrong screen. So this is the safe operating space in the center. This zone of uncertainty of the orange is saying, look, this is a warning zone. And then anything over and above the red line is really the danger zone. We're well beyond the safe limit and we know that this is a problem. And I think what this diagram shows us at a glance is why having carbon tunnel vision, or that's a new term, those of you who haven't come across it, you know, that real singular focus on carbon and climate change is so dangerous, because yes, climate change is really mission critical at the moment and we are well outside the safe operating space. But actually, if you look, biogeochemical flows, and I'll talk about what that means in a minute, and biosphere integrity are already well into the red zone. And so even if we stopped burning fossil fuels today and emitted no more greenhouse gas emissions, but continued to have impacts on biogeochemical flows and biosphere integrity, we wouldn't end up with a Holocene like Anthropocene, and we would still have irreversible catastrophic global change. And so it's really mission critical that we think about this whole picture when we're making decisions. So I'm just going to talk through for about 10 minutes what each of these planetary boundaries are, not in a huge level of detail and not in the numbers, but just so that we have a really better understanding of the broad picture. And then we're going to jump into some breakout rooms and work through what that might actually look like given a few different scenarios. So the first one, climate change, which we talk a lot about, there are two components to this planetary boundary. They talk about the concentration of carbon dioxide in the atmosphere, but also a change in a term called radiative forcing. Radiative forcing is basically just how much solar energy reaches the Earth's surface, and that is impacted by the amount of carbon dioxide and other greenhouse gases in the atmosphere, but also things like how reflective Earth's surface are. So if we cut down forests or if we melt ice caps so that there's less white and more dark blue ocean, that has an impact on radiative forcing, but also air pollution. So while air pollution is really bad for human health, it's actually pretty good for climate change. And so the more air pollution, the less energy comes to the surface. So those are the sort of two planetary boundary indicators under climate change. Novel entities is a really all-encompassing term, and it basically means man-made things that are either toxic or long-lived. So long-lived is things like plastics, and toxic covers heavy metals, chemical pollution, any radioactive waste is all covered by that. And so as you can imagine, that's a really broad component to try and put into a single or one or two metrics. And so if you look at that wedge, it actually, it shows as silver or grey rather than a particular colour. And that's because they haven't agreed on a metric that they can use to measure or to set a boundary against. However, it's almost certain that we're in the danger zone for that outside of the red circle, and a study providing a lot of evidence for that, still without a metric, was released earlier this year to just provide that evidence that we are beyond that limit. Stratospheric ozone depletion, so that's something that I think we all know a lot about in New Zealand and Australia. I think there's a few people dialed in from Australia today. But that's basically a measure of the thickness of ozone where there is this hole. It's not actually a hole, but a thinning of the ozone layer. And so the things that impact that are the release of CFCs and refrigerants. But that's actually the good news story in the planetary boundaries, because we are A, in the safe operating space, and B, moving away from the danger zone. And that's, I guess, shows the effectiveness of global cooperation, or the effectiveness global cooperation can have. So the Montreal Protocol took us from the danger zone to back into that safe zone. So that's really positive, and I think it's really neat that this is included in the framework, because it is important to know that we can actually come back from beyond the limits. Atmospheric aerosol loading is basically a fancy way to say air pollution, and it's measured in how much light as a fraction or solar radiation, sorry, it shouldn't say light and solar radiation there, reaches Earth's surface. And so atmospheric aerosol optical depth is the term, of 0 means all of the light comes through, and 1 means it's so polluted that almost no light comes through. So again, this one is greyed out. It is actually measurable at local scales, but the variability across the planet is so high that they haven't got a single planetary boundary at a global scale, but still include it because it is so critical at that global scale, both to human health and because of the impacts and interactiveness with these other planetary boundaries. Ocean acidification is really directly correlated to how much carbon dioxide is in the atmosphere, but it's specifically in the Planetary Boundaries Framework, because the more acid the ocean is, the less that marine species can create calcium carbonate. And calcium carbonate is the basic material for shells, but also for skeletons, like for coral. And so without the ability to make this, we would just have this huge mass extinction in the ocean. The metric is aragonite saturation, but I don't expect anybody to remember that. Nitrogen and phosphorus runoff into water is basically what's captured by biogeochemical flows, and you can actually even see in the diagram on the left that those are slightly separated, so they're measured separately as two different metrics, but both nitrogen and phosphorus cause something called eutrophication, which, if you haven't come across the term before, basically means because there's nitrogen and phosphorus are both really essential to growth of plants, and so if you have too much of them, then you get too much growth, and so you get this huge algal bloom, and that kills off the oxygen into the water, and so you get these dead zones in waterways. Now that's really critical in places like New Zealand and Australia, where we have a lot of agriculture, because we're getting a lot of it in our rivers and our lakes, but actually at the planetary boundary scale, it's really looking at that global scale and how much of that nitrogen and phosphorus is going out into the oceans as well. And at the moment, there are dead zones that if you brought them all together, they're sort of spread out around the planet, but if you brought them all together, they'd create an area bigger than New Zealand. So it's pretty significant already. And one of the past global mass extinctions has actually been caused by too much phosphorus runoff into the oceans. So we're in potentially the 6th mass extinction. The dinosaurs dying out was another mass extinction, but there have been others, and so this has been a cause of one of the ones in the past. Fresh water consumption, the planetary boundary exists because of the changes that human activity are having on global hydrological flows around the planet. So, when we're moving the way water travels from one place to the other, extracting a lot of water over here and then using a lot somewhere else, changing how much water is applied to land in places that there wasn't much rainfall, cutting down rainforests and things like that, are all having this massive impact. But to simplify the ability to put a boundary against it, the planetary boundary is just around freshwater consumption, how much we're using. And although this diagram looks like we're way below that danger zone, actually this diagram was updated most recently in 2015, and since then we're really much closer to it. So it's likely that we're really in the danger zone now. Again, with land system change, this is a really complex challenge where the ability of the Earth system to function is really driven by a lot of different land system types, so wetlands and grasslands, but the boundary is about the original forest area remaining, rainforest area remaining, and that's because that is the most critical land system type, but again, it's that simplification so that you can have it as this sort of reasonably straightforward framework for global health. And finally, biosphere integrity. So there are 2 indicators in the biosphere integrity limit boundary. One is the functional diversity, so how diverse our different ecosystems are, and the other is species extinctions. So we can have about 10 extinctions per million species in the world each year within the safe limits. We're somewhere between 100 and 1,000 extinctions per million species, so we're way outside the limit.